Alright, welcome to this video about deterministic finite automata, DFA. Yeah, this will be our first finite state machine that we will learn about. Deterministic finite automata, for short DFA. Don't worry about this word yet, especially this deterministic. I will explain this later in the video. For now, just what is a DFA? You can think of a DFA as a small machine, a small computer basically, that accepts a string as an input. It gets a string as an input, then it does some calculations, and in the end it will output a boolean. That's a truth value, just true or false. Yeah, and you can think of these truth values as accepting or rejecting the string. Yeah, so basically think of it as a machine that verifies a string. It gets a string and then either it does some calculations first and then accepts the string or rejects the string. Okay, let's look at an example. Yeah, so this is how a DFA looks like. What do we see here? We see some circles. Every circle is a state, so we have 3 states. Yeah, don't worry about the pink circle yet. We have 3 states. Then we have one state that has a green arrow. We will always have one such state with a green arrow. This is how I denote the starting state. So there's always one starting state, and in this case it's this one. This is the starting state. And as I said before, we will get a string as an input, yeah, and then we will read the string letter by letter and just follow the arrows. So let's see how this works. So for example, let's look at the word BAB. Yeah, we start in the starting state and now we read BAB letter by letter. So the first letter is a B, so we follow the B arrow from this state. This leads to itself. Yeah, it's just a loop. So we end up in this state again. The next letter is an A, so we follow the arrow with A. So we go to this state. Now we are here. And now we read the final B, so we do a loop again, so we end up in this state. Yeah, and since this state has a pink circle, we accept the word BAB. Yeah, so that's what we will do. We will read the whole word letter by letter, and if we end up, like after we've finished reading all the symbols, if we end up in a state that has a pink circle, which is called an accepting state or finishing state, then we will accept the word. We will accept the string BAB. So BAB gets accepted. Yeah, let's just write it like this with this green check mark here. And now let's look at another example. For example, the word ABBA. Yeah, so we start in the starting state again. We follow, since the first letter is an A, we follow the A arrow. So we switch the state to here. The next letter is a B, so we do the B loop. Then we have another B, so we do the B loop again. And the final letter is an A, so we switch the state and we land here. And we finished reading this word, ABBA. And since this state doesn't have a pink circle, it's a rejecting state. So we reject the word ABBA. So we write it with a red X. This is rejected and this was accepted. Okay, now that we have a basic idea of how a DFA works, let's go a little into detail. We cannot give just any string to this DFA. We can only give certain strings to it because it doesn't have, for example, it doesn't have an outgoing C arrow or D arrow. Yeah, it just has A and B arrows everywhere. So every DFA is somehow connected to an alphabet. Yeah, we fix an alphabet. In this case, it's the alphabet AB. Yeah, and once we fix this alphabet, we have to make sure that our deterministic finite automaton has in every state, for every symbol from this alphabet, precisely one outgoing edge, one outgoing arrow. Yeah, we see in this state we have one outgoing A arrow, one outgoing B arrow, no more and no less. Yeah, and as well here, one outgoing A arrow and one outgoing B arrow, and the same here, we have one outgoing A and one outgoing B arrow. Yeah, And this is why it's called a deterministic finite automaton, because when it's reading such a word, it's always determined where it will go, yeah, because there's precisely one outgoing arrow for every symbol, yeah. Whatever the word is, it's always determined how we will go and in which state we will end up when we have finished the word. Yeah, that's why it's called deterministic, because it's all already determined. Okay, now we know into this DFA we can put any word that consists of the letters A and B. And we have actually a notation for this. Remember last time? The set of all strings that can be made up from one alphabet is denoted by this alphabet with a star. Yeah, so in this case, this is the set of all strings that we could put into here. And now imagine we would actually do this. We would actually put every single string once into this into this deterministic finite automaton. And then, well, some of them would get accepted and some of them would, yeah, all others would get rejected, yeah. And in this way, this DFA or any DFA will define a formal language, namely the set of strings that gets accepted by this finite automaton. Yeah, so it will define a subset, let's call it L. It will define a subset of the set of all strings. Yeah, so it defines a language in this way. The language is just the set of words from A, B star that gets accepted by this automaton. And usually you will denote such an automaton by this letter A, this funny capital A, yeah. So you can say this automaton is A, and then you write L of A is the words from A, B star that get accepted by A. Yeah, so this is really important. This is how we will mostly think of deterministic finite automata as tools that can define formal languages for us. Every deterministic finite automaton defines precisely one language, that is the words that get accepted by this automaton. So in this case, the BAB, it got accepted, so instead of this green check mark, now we can also write it's an element of L of A, yeah? BAB is an element of the language that gets recognized by this automaton because, well, we ended up in an accepting state when we read BAB. And ABBA, it got rejected. We ended up in this state, it got rejected. So it is not element of this set. Yeah, it's not element of L of A. Okay, and just for fun, let's take a moment and let's think what is the language that gets accepted by this finite automaton? I mean, how can we describe the set of words, the set of strings that gets accepted? Well, we see here, as long as we read only B's, we will stay in this state, and this is not accepting. So if our word consists only of B's, we will reject. But if it has one A, and even if it has several B's more after that, we will accept. But if it has another A, a second A, we will reject. And then whatever we read after that, doesn't matter, we will still reject it. So we only end up in this state if our string contains precisely one A. Yeah, so the language accepted by this automaton, that is the set of all strings from A, B star that fulfill this condition that they have precisely one A. Alright, and let's close out with one final definition for this video. The definition of a recognizable language, or a language recognized by a DFA. Okay, so I'm running almost out of space, it's here. L is DFA recognizable if there is a DFA called A such that L is the language recognized by this DFA, yeah? So this is an example for a recognizable language, yeah? The strings containing only A's and B's who contain precisely one A. This is a recognizable language. Okay, and in the next video we want to get a feeling for this DFA recognizable, yeah, for this property. what kind of languages are DFA recognizable. We will look at some more examples so we get a feeling for this. So see you in the next video.